Right, welcome to the deep dive. You know why you're here, right? To get to the juicy stuff without the fluff. Today we're tackling adversarial search, often called games in AI.
Yeah, and it's more than just, algorithms playing games. It's really about how AI systems can plan strategically, especially when they're up against other intelligent agents.
Exactly. And we're going deep with this one. We've got these super detailed lecture notes on adversarial search, and we're going to pull out the core insights.
The mission here is to understand how AI tackles situations where there are multiple players, each with their own goals that might even clash. And we'll dig into the techniques they use to figure out the best strategies.
So, first things first, what exactly are we talking about when we say adversarial search?
Well, it's all about how an AI finds its way through a problem. But here's the catch. It's not just solving a puzzle in isolation.
Right, it's not like those classic AI maze solving examples.
Exactly. In adversarial search, you have to plan your moves while also thinking about what your opponent's going to do. And they're trying to do the same thing to you. Imagine a maze where the walls are constantly shifting because someone else is moving them.
Okay, I can see how that ups the ante. So, we're not just talking about simple mazes, we're talking about environments with multiple players, right? What do you call those?
Multi-agent environments. You've got multiple agents all in the same space trying to achieve their objectives. But in adversarial search, their goals are at odds, making them opponents.
So, it's like a constant game of chess, always thinking a few steps ahead.
Yeah, that's a good analogy.
Mm.
And speaking of chess, that brings us to the different types of games we see in AI. One category is perfect information games.
Perfect information, like you know everything that's going on.
Exactly. All players have complete knowledge of the game state. They see everything. Think chess, checkers, go. No hidden cards or surprise attacks.
Okay, so what's the opposite of that?
Imperfect information games. Here, some information is hidden. Like in poker, you don't know what cards your opponent's holding. Battleship, you don't know where their ships are. Even tic-tac-toe could be considered imperfect information if you don't know your opponent's strategy from the start.
Right, so there's an element of uncertainty, a fog of war. What other ways do we classify these AI games?
Another important distinction is between deterministic and non-deterministic games. Deterministic games have fixed rules, no randomness. Every action leads to a predictable outcome. Chess, checkers, go, even tic-tac-toe, all deterministic.
So no dice rolls or lucky draws.
Exactly. On the other hand, non-deterministic games, sometimes called stochastic games, have elements of chance or luck. Think dice rolls in backgammon, drawing cards in poker, or the random events in Monopoly.
Ah, so even if you make a perfect move, you could still get screwed by chance. Makes it a lot trickier for the AI.
It does. Now, our lecture notes dive into a specific type of adversarial search called zero-sum games.
Zero-sum games, what makes them special?
In these games, it's pure competition. One player's gain is the other player's loss. It's a win-lose situation, no compromise. Like a pie, if you get a bigger slice, the other person gets a smaller one.
Got it. So there's no way for both players to benefit.
Nope. One player's trying to maximize their score while the other's trying to minimize it. We often use the term ply to refer to a single move by a player.
Makes sense. So what are some examples of these zero-sum games?
Chess and tic-tac-toe are classic examples. But lecture notes also talk about this thing called embedded thinking in zero-sum games.
Embedded thinking, huh? Sounds deep. What's that about?
Well, in these games, you can't just think about your own moves. You have to think about what your opponent's going to do in response and what you'll do after that and so on. It's like a chain of predictions and counter predictions.
So you're trying to outsmart your opponent by anticipating their every move.
Exactly. You have to reason backwards from potential end states to figure out the best sequence of moves, all while considering what your opponent might do to mess up your plans.
Sounds exhausting. So how do we even begin to represent this complex thinking process for an AI?
That's where problem formalization comes in. It's a way to break down the game into elements that an AI can understand and work with. We start with the initial state, which is how the game looks at the very beginning.
Okay, like the starting position in chess. What else do we need?
We also need to know player, meaning whose turn it is at any given moment. Then there's actions, which tells us all the legal moves available to the current player.
So we've got the starting point, who's playing, and what they can do. What's next?
Then we have result, which describes what happens when a player takes a certain action. Basically, it tells us what the new game state will be.
So it's like cause and effect. If I do this, then that happens. Okay, and how do we know when the game is over?
For that, we have the terminal tests. This function tells us if we've reached a state where the game ends, like a win, loss, or draw.
Right, because the AI needs to know when to stop searching.
Exactly. And finally, we need a way to determine who won or lost, and by how much.
I'm guessing this is where points come in.
Yep. That's where the utility AV function comes in. It assigns a numerical value to the final state for each player. It's like a scorecard. For example, in tic-tac-toe, we might assign +1 for a win, -1 for a loss, and 0 for a draw.
So we've got all the pieces. The starting point, the players, their moves, what happens when they move, how we know the game ends, and how we score the outcome. Sounds like a solid system.
It is. And to represent all these possibilities visually, we use a game tree.
A game tree. What's that?
It's basically a diagram showing all the possible ways a game can unfold. It starts with the initial state and then branches out to show all the possible moves for each player and then all the possible counter moves and so on.
So it's like a map of all the potential paths the game could take.
Exactly. Each node in the tree represents a game state, and the edges connecting the nodes represent the moves. For tic-tac-toe, we'd start with the empty board, then show all the possible first moves for X, then all the possible responses for O, and so on, until we reach all the possible endgames.
Okay, I can see how that could get pretty big, even for a simple game like tic-tac-toe.
You're right. And for more complex games like chess or Go, the game tree can become astronomically huge, with billions and billions of possible paths. This brings us to the challenge of how to search through this massive tree efficiently to find the best move.
Right, because checking every single possibility would take forever. So what's the solution?
One of the foundational algorithms for this is the Minimax algorithm.
Minimax, huh? Sounds intriguing. What's the idea behind it?
It's all about minimizing the maximum possible loss, hence the name Minimax. Imagine two players, Max and MIN, playing a zero-sum game.
Okay, Max wants to win, and MIN wants to make Max lose.
Exactly. The Minimax algorithm assumes both players will play optimally. So Max will try to choose moves that lead to the highest possible score, while MIN will try to choose moves that lead to the lowest possible score for Max.
So it's like playing against a perfect opponent, always assuming they'll make the best possible move.
Exactly. Now, the way the algorithm works is it explores the entire game tree using a depth-first search, going all the way down to the terminal nodes where the game ends. At those terminal nodes, we know the outcome, win, loss, or draw, and we have the utility values.
Right, because at the end of the game, we can see who won and by how much. So how do we use that information to figure out the best move from the starting position?
Well, the algorithm works its way back up the tree, assigning values to each node based on the values of its children. So if it's Max's turn at a node, the value of that node will be the maximum of the values of its children.
Because Max wants to choose the move that leads to the best possible outcome.
Right. And if it's MIN's turn, the value of the node will be the minimum of the values of its children.
Because MIN wants to choose the move that leads to the worst possible outcome for Max.
Exactly. This backtracking process continues all the way up to the root node, which represents the current state of the game. The value assigned to the root node is the best possible outcome for Max, assuming both players play perfectly.
Okay, that makes sense. So Minimax gives us a way to find the optimal move, but it sounds like it could be computationally expensive, especially for complex games.
You're right. The time complexity is O of B to the power of M, where B is the branching factor, the average number of moves at each step, and M is the maximum depth of the tree. This means that for games like chess or Go, where the game tree is enormous, Minimax can be incredibly slow. It might take years or even centuries to explore all the possibilities.
Wow, so Minimax is good in theory, but not always practical. What can we do to make it more efficient?
That's where alpha-beta pruning comes in. It's a clever optimization technique that can significantly reduce the number of nodes we need to explore.
Pruning, so we're cutting off some branches of the tree.
Exactly. The idea is to avoid exploring branches that can't possibly lead to a better outcome for either player. And we do this by keeping track of two values, alpha and beta.
Alpha and beta, what are those?
Think of them as bounds. Alpha is the best or highest value that Max has found so far along the current path. It's like a guarantee Max knows they can achieve at least this score.
Okay, so alpha is like a minimum score for Max. What about beta?
Beta is the best or lowest value that MIN has found so far along the current path. It's the highest score that MIN is willing to allow Max to achieve.
So beta is like a maximum score for Max from MIN's perspective.
You got it. Now, the key idea is that if alpha ever becomes greater than or equal to beta, we can stop exploring that branch of the tree.
Why is that?
because it means we found a situation where Max already has a guaranteed score that's better than anything MIN is willing to allow.
Yeah.
So there's no point in exploring that branch further.
So we're cutting off branches that are guaranteed to be worse than something we've already found. That's pretty clever.
It is. And by doing this repeatedly, we can prune away huge chunks of the game tree, making the search much more efficient. Now, how much we can prune depends on something called move ordering.
Move ordering, what's that about?
Well, the order in which we consider the possible moves at each step can affect how effective the pruning is. In the worst case ordering, we might not prune much at all. This usually happens when we consider the best moves last.
So we end up exploring almost the entire tree, like with regular Minimax.
Exactly. But in the best case ordering, where we consider the most promising moves first, we can prune away a lot of branches.
So it's like finding a really good move early on, which allows us to rule out a bunch of other possibilities.
Exactly. And there are various techniques for trying to achieve good move ordering. One is to use heuristics, rules of thumb, based on our knowledge of the game.
So for example, in chess, we might prioritize moves that capture pieces or threaten the opponent's king.
Exactly. We could also use techniques like iterative deepening, where we do a shallow search first to identify promising moves, and then use that information to guide our deeper searches.
So it's about using our knowledge of the game to make smarter decisions about which moves to explore first.
Exactly. And all of this is about making these algorithms efficient enough to handle the complexity of real-world problems.
So to wrap things up, we've learned that adversarial search is all about planning in the face of competition, where multiple players are trying to achieve conflicting goals. We've seen how games are categorized, from perfect information to non-deterministic games, and how the concept of a zero-sum game captures the essence of pure competition.
We also dove into the nuts and bolts of how AI tackles these problems, from representing the game using game trees to using algorithms like Minimax to find the best moves.
And we discovered the power of alpha-beta pruning, a technique that makes the search process much more efficient by cleverly cutting off branches that aren't worth exploring.
The takeaway here is that efficiency in AI isn't just about brute force computation, it's about intelligently structuring problems and finding shortcuts.
It's like that old saying, work smarter, not harder. And this applies not just to AI, but to problem solving in general. Well, this deep dive has given me a whole new perspective on how AI can tackle complex strategic challenges.
Glad to hear it.
And it makes you think, doesn't it? How often in our own lives are we engaged in some form of adversarial search, even if we don't realize it? Whether it's negotiating a deal, competing for a promotion, or even just trying to outsmart the traffic on our way to work.
Interesting point. We're constantly making decisions based on our predictions of what others will do.
Exactly. So maybe understanding these AI techniques can give us a slight edge in our own strategic games, something to ponder.
Food for thought indeed.
Well, thanks for joining me on this fascinating journey into the world of adversarial search. Until next time.
It's been a pleasure.